Hi, and welcome to the Graphisoft EcoDesigner Star Energy Efficient Building Design video series. This movie is titled Building Energy Model Calibration and shows how to validate your building energy model, or BEM for short. There are two types of building energy model calibrations. The first is used to validate the software application that runs the building energy simulation. This software validation is typically carried out by the software developer. The validation result is usually displayed on the website of the developer. For example, Graphisoft EcoDesigner Star is compliant with the ASHRAE 140 simulation standards. The second calibration type is design model validation. To be able to get an accurate energy evaluation, it is crucially important to provide appropriate and very precise input for the calculations. Not all architectural designers are fully familiar with all the energy-related characteristics and properties of the design projects. To make sure that all the energy-related characteristics of the zones, structures, and openings, as well as the operation profiles, etc., are correctly set and modeled, it's worth performing the model calibration for every BEM. This can be done with the help of a reference model with a known energy performance. The software validation typically consists of numerous building energy models, or cases, each of which is simulated with the software being tested. The calculation results are then compared with benchmark values for each case. Benchmark values are provided as part of the standard. The standardized cases cover a vast range of energy modeling scenarios. Therefore, if every case is valid, then proper software operation is ensured and building energy simulation standard compliance is achieved. In this video clip, we will present a building energy model from the ASHRAE 140 standard. Since the workflow used to validate this model is quite similar to the workflow that should be applied to calibrate all other design models as well, this standardized case can be used for dual purposes: to demonstrate the design model validation workflow in general, to illustrate the explanation regarding the ASHRAE 140 compliance testing of the EcoDesigner Star software. By calibrating your building model, you will ensure that your building energy model is correctly configured and all the reports you generate are accurate. The reason for calibration is to obtain the reference building data for the calibration process. The reference building should be a similar building to the one you're designing. For example, if you often design residential buildings in a certain location, then you're probably already familiar with how buildings of similar size and function perform in that particular climate. If you do not have a suitable reference building in your archives, then rely on energy-related statistics or case studies from publicly available sources. Look for the energy performance documentation of buildings similar in size and operation to the one you're about to design. The NREL reference building model's energy data, compiled and published by the United States National Renewable Energy Laboratory, NREL, is, for example, a great source of building energy performance information. It contains the statistical energy consumption data of numerous building types as built in several different locations. The data is grouped according to climate, building construction, size, and operation profile, which includes residential, office, retail buildings, and so on. Samples from this vast database can be used to validate building energy models outside the United States as well. A model from a building energy simulation standard can also be used as a reference building to perform the calibration of your design. In this presentation, we will use one of the ASHRAE 140 standard building models to show you how to calibrate a building energy model, as well as demonstrate that EcoDesigner Star complies with the ASHRAE 140 standard. The official name of the ASHRAE 140 standard is Standard Method of Test for the Evaluation of Building Energy Analysis Computer Programs. This is the internationally accepted validation procedure for high-end building energy performance analysis software. ASHRAE 140 is referenced by all significant green building rating standards, for example LEED, Green Star, BREEAM, CASB, DGNB, and Section J of the Building Code of Australia. The ASHRAE 140 standard documentation contains over 100 various cases, architectural tests called building envelope tests, and building system tests for various heating, cooling, and ventilation system setups. If a computer application can correctly simulate all ASHRAE 140 test cases and provide appropriate results, then these simulation results are approved as a basis for a building energy performance rating as prescribed by LEED, BREEAM, Green Star, and others. All ASHRAE 140 test cases relate to one of the so-called base cases. For example, there are 2 envelope test base cases. These base cases are modified and listed as more complex subcases, which all originate from one of the base cases. All the energy scenarios described in the base cases, as well as in the subcases, must be properly simulated by the computer application in order to obtain approval and receive standard compliance certification. In this example, we'll present one of the envelope tests of the ASHRAE 140 standard. This will be the so-called SunSpace test, and its case number is 960. Let's have a quick look at the description of this particular case first. The standard defines the detailed geometry of the building model on which the test must be run. Below, all the corresponding material properties are also listed in tables. In the case of the SunSpace test, 2 thermal blocks must be considered: a sun zone with a window and a back zone behind it. The parameters defined in the ASHRAE 140 standard must be input into the software application precisely. After executing the energy simulation, the calculated results must meet the results defined in the standard. In the case of the SunSpace test, the following calculation results must be shown: total annual cooling and heating energy for the back zone, heating and cooling peak loads for the back zone, minimum, maximum, and annual mean temperatures in the sun zone. The back zone is a so-called conditioned space, and the sun zone is an unconditioned space. These terms will be explained shortly. After the building energy simulation is completed by the software application being tested, the relevant results must be entered into a standard result spreadsheet, which you can see on the screen. Each row represents a test case defined by a 3-digit number. Today, we'll present case 960. This chart of the standard result spreadsheet, for example, is used to validate the annual heating loads. The standard table contains the calculation results of other software applications for reference. The last 2 columns contain the minimum and maximum values as calculated by the other reference software. These 2 values define a range for the acceptable results. To be able to achieve standard compliance, the results calculated using the software application being tested must be within this range. There are additional tables for annual cooling loads, peak heating and cooling, and so on. All relevant calculation result data for each test case must be processed using the validation method described above. Let's display the building model of case 960 of the ASHRAE 140 standard in ArchiCAD. The building model is pretty simple. It contains only 2 thermal blocks. The sun zone is a heavyweight construction, while the back zone is a lightweight structure. The Energy Model Review palette helps to visualize the 3D geometry, as well as all the energy-related characteristics of the building. The Thermal Blocks page of the palette represents the zoning of the energy model. The Structures page lists all the opaque structural elements with their relevant properties. The Openings page presents the energy-related characteristics of the fenestration. Let's have a closer look at the specifications of the back zone as defined by the ASHRAE 140 standard. Here you can see the geometry of the zone, while the following page describes the various structures' thermal properties. The names of the individual skins of the composite structural elements with their thickness, thermal conductivity, heat capacity, and density are all precisely defined in the standard. Using the advanced modeling tools of ArchiCAD, it was really quick and easy to create the building model according to the ASHRAE 140 standard specifications. Here you can see the structures list of the Energy Review palette. It lists all the composite structures used in this test case with the relevant properties of their skins. The thickness, thermal conductivity, heat capacity, and density of the skins of this external wall, for example, exactly match the values defined by the ASHRAE 140 standard. The openings characteristics are also precisely described in the standard. Switch to the openings page of the Energy Review palette of EcoDesigner Star to see all the input parameters the program uses to describe the fenestration in test case 960. We can use the openings page to scroll, rearrange, filter, and sort all the relevant properties of the openings. Let's have a look at the infiltration rate prescribed in the ASHRAE 140 standard. The air change per hour is defined as 0.5, a constant value for both thermal blocks. In EcoDesigner Star, however, the infiltration model is pressure-driven. In other words, it's not constant. To model constant infiltration with EcoDesigner Star, we must define it as natural ventilation. We've set a natural airflow at a steady 0.5 ACH rate for the entire year. This way, we fully meet the simplified, constant infiltration modeling requirements of Case 960 of the ASHRAE 140 standard. Proceed by having a closer look at the external and internal surface coefficient settings for the individual structures as well as for the overall building energy model. Use the U-value calculator dialog to enter the combined surface heat transfer coefficients for the steady-state calculation of the structure's U-values. In addition, enter the external combined and internal convective surface heat transfer coefficients for the dynamic energy simulation via the surface heat transfer dialog of the Environment Settings panel. Let's continue and have a closer look at the operation profile of the back zone, which is a so-called conditioned space. By definition, a conditioned space is an enclosed space within a building where there's intentional control of the internal temperature. It's maintained within a temperature range defined by limit temperatures, using natural, electrical, or mechanical means. In layman's terms, this means that there are certain internal temperature requirements for the thermal blocks that must be met with the help of heating and/or cooling systems. In the case of an unconditioned space, the internal temperature is not controlled. Here you can see how the ASHRAE 140 standard defines the thermostat control strategy, limit temperatures, for the back zone of Case 960. The heating turns on if the internal temperature drops below 20 degrees Celsius, and the cooling turns on if the internal temperature rises above 27 degrees Celsius. Let's view the operational profile in EcoDesigner Star that contains the internal temperature limits for the back zone. Display the Operational Profiles dialog and select the ASHRAE profile from the list. Let's open the Daily Profile Editor dialog to have a closer look at the daily profile settings. The upper diagram can be used to define the maximum and minimum limit temperatures beyond which heating or cooling must be used for every hour of the day. The daily profiles defined with this editor must then be assigned to the days of the reference year. Let's also review the constant internal heat gain requirement prescribed by the ASHRAE 140 standard for test case number 960 as internally generated sensible heat. It's defined to be a continuous 200 watts throughout the entire year, 60% of which is radiative, 40% convective, and 100% sensible. Let's see how to set these parameters in EcoDesigner Star. Open the Daily Profile Editor once again, and view the lower diagram representing the characteristics of internal heat gain. Checkmark the equipment option, and enter 4.17 watts per square meter for every hour of the reference day. Then use the Operation Profiles dialog to assign this daily profile to every day of the calculation year. If 4.17 watts per square meter is multiplied with the 48 square meter conditioned area, then the result is a steady 200 watts of internal heat gain throughout the entire reference year as prescribed by the standard. As the last step of setting the input parameters for the internal heat gain calculation, open the Energy Simulations Options dialog and enter 60% for the radiation part of the internal heat gain to precisely match the standard prescription. Note, the Energy Simulation Operations dialog of EcoDesigner Star is also used to define the latent part of the internal heat gain. It is set to 0 for case 960. Let's proceed and see how to run the building energy simulation, this time in demand calculation mode. Let's open the Building Systems dialog. Please note that a heating and cooling system is already created and added to the back zone. Define these systems as not yet specified, in which case there is no need to define any additional system parameters. In order to determine the heating and cooling demands, we must make EcoDesigner Star carry out the energy simulation assuming that the heating and cooling systems are capable of satisfying all the requirements with 100% efficiency. The building system type in EcoDesigner Star defined for demand calculation is called Not Yet Specified. Not yet specified building systems fulfill all heating or cooling demands as they arrive during the hourly building energy simulation throughout the entire reference year. The calculated hourly heating and cooling demands are recorded by the program and displayed on the building energy evaluation reports. This demand calculation output can be used to determine the actual building system's characteristics. To set up the demand calculation, assign these not yet specified building systems to the thermal zones. Note, EcoDesigner Star is capable of modeling building systems in a very detailed way. Case 960 of the ASHRAE 140 standard, however, only requires demand calculation. Let's take a look at the characteristics of the sun zone. It has 2 windows and a common wall with the back zone. The geometry, material specifications, and additional relevant properties of the sun zone were input into EcoDesigner Star in accordance with the ASHRAE 140 standard. A workflow similar to this was explained earlier in detail as part of the presentation of the back zone's characteristics. For example, you can see the opaque building energy model element's relevant characteristics displayed on the Structures page of the Energy Model Review palette. Let's take a closer look at the operation profile of the sun zone. This thermal block is a so-called unconditioned space. By definition, an unconditioned space is an enclosed space within a building that does not meet the requirements of a conditioned space. These spaces have no control over thermal conditions, but receive thermal energy from adjacent spaces. In other words, these spaces do not have any building system assigned to them that would regulate the internal temperature. Without any minimum or maximum limits defined, internal temperature changes without constraints. This phenomenon is called free-float internal temperature. Let's see how to specify an unconditioned space in EcoDesigner Star. Here you can see the previously created ASHRAE Sun Zone operation profile. From the Daily Profile Editor, we can see that there are no maximum or minimum temperature limits defined for this operation profile. Naturally, no building systems are assigned to the unconditioned spaces either. There are no internal heat gains in the sun zone of case 960, but the previously discussed steady airflow is added to it to represent the infiltration defined in the ASHRAE 140 standard for this test case. So now let's run the building energy simulation by pressing the Start Energy Simulation button. It takes a couple of seconds to complete the calculation, and the results are displayed on the screen. The next step is to specify the chapters we wish to include in the Building Energy Evaluation PDF report. We can select the required chapters on the left under the Report Chapters page of the dialog. In case 960, since only the energy demand calculation is required by the ASHRAE 140 standard, many of the chapters, for example fuel consumption, performance rating, etc., do not apply and therefore should not be included in the documentation of the test case. Let's go through the chapters that are relevant for our example one by one. First, select chapters that contain project-level results. Checkmark the key values in the Project Energy Balance chapters. Then scroll down to select the Thermal Blocks chapter as well. Secondly, select chapters that contain thermal block level results. The Thermal Block Energy Balance and Thermal Block Key Values chapters display important energy performance and comfort data, such as total annual energy flows, peak demands, as well as annual internal temperature averages and extremes. The Daily Temperature Profile chapter displays the hourly temperatures inside the selected thermal block on any selected day of the calculation reference year. There are different diagrams for the different thermal zones and days, any of which can be selected for documentation. Use the Chapter Settings panel to select the thermal block and the day of the year. The corresponding internal temperature profile instantly appears among the chapters to be documented on the preview area on the right side of the evaluation report dialog. Although not yet specified building systems were used for the demand calculation in this example, it's a good idea to also include the energy consumption by targets and energy consumption by sources chapters in the report, since these chapters provide information about the quality of the building energy model and simulation data processing. Let's proceed and save the report as a PDF document by selecting the Save as PDF button in the lower right corner of the Evaluation Report dialog. Let's customize and then save an Excel spreadsheet report as well. The report in Excel spreadsheet format provides a more detailed breakdown of energy analysis input and output data that can be easily post-processed. Similarly to how the content of the PDF Energy Evaluation Report can be customized, it's also possible to specify the chapters we wish to include in the Excel spreadsheet report. This time, let's select the thermal block's detailed inputs, thermal block key values, and the monthly and hourly thermal block results for the documentation, then click OK to save the spreadsheet. Use the previously created PDF evaluation report to review the energy simulation results chapter by chapter. Looking at the Project Key Values chapter, we see basic structure geometry and performance information displayed on the right. Please note that the dedicated ASHRAE 140 climate data file was used for this simulation. The project energy balance displays the sum of all the individual thermal block energy balances. The thermal block key values are also part of the evaluation report. Let's see the key values of the unconditioned sun zone first. In the case of the sun zone, the internal temperature data on the left side of the sun zone key values chapter is the most important. Then scroll down to display the key values of the conditioned back zone as well. For the conditioned back zone, the annual heating and cooling energy values is the data we are after, and it's displayed on the right side of the back zone key values chapter. Let's see the thermal block energy balances next. On the energy balance diagram of the unconditioned sun zone, the solar gain in yellow is counterbalanced only by the transmission and the airflow displayed in blue and brown respectively. On the energy balance of the conditioned back zone, the heating demands appear in red on the supply or top side of the diagram, while the cooling demands are shown in the darker greenish blue as emitted energy on the bottom side of the energy balance diagram. The HVAC design data table contains very important demand calculation output. It displays the annual and peak heating and cooling loads of the conditioned thermal block or back zone. This building system sizing data is necessary for energy modeling and for HVAC design alike. Let's also review the detailed simulation data presented by the Excel spreadsheet evaluation reports. Based on the custom report content specified by the user, a project data Excel spreadsheet is generated alongside the separate spreadsheets dedicated to each thermal block. The first page of the thermal block result data spreadsheets is the detailed inputs page. Let's open the second page, which contains the detailed monthly results. The annual heating and cooling loads are displayed here. Annually, 2,558 kilowatt hours are required for heating, and 658 kilowatt hours are required for cooling for the back zone in the example project. For the next step, let's use the spreadsheet of the ASHRAE 140 standard that contains the reference simulation results. This is a copy of the Excel file that was presented at the beginning of this movie. Besides the standard's reference values, this sheet now also includes the EcoDesigner star calculation results for all the ASHRAE 140 test cases. The test case we investigated, number 960, is now highlighted on the screen. Our calculated annual heating load was 2.56 megawatt hours for the back zone. As you can see, The standard reference result range is between 2.3 and 3.3 megawatt hours. This means that the calculation performed by EcoDesigner Star is within the acceptable range defined by the ASHRAE 140 standard. Let's look at the annual cooling load as well. The EcoDesigner calculation result is 0.66 megawatt hours. The acceptable range prescribed by the standard is between 0.41 and 0.8 megawatt hours for case 960, so the EcoDesigner Star calculation result meets the ASHRAE 140 standard requirements. Let's proceed to validate the peak cooling load and peak heating load calculation results. Display the thermal block key values page for the calculated annual hourly integrated peak heating load, which is 2.7 kilowatts. The annual integrated peak sensible cooling load, according to the EcoDesigner energy simulation results, is 1.18 kilowatts. Let's compare these values with the results provided by the standard. The peak heating load must be between 2.4 and 2.8 kilowatts. So the EcoDesigner Star calculation is yet again in the acceptable range. Same applies for the peak cooling load, which must be between 0.9 and 1.4 kilowatts. Please note that EcoDesigner Star is the only software solution native to the architectural design environment. All other dynamic building energy analysis software solutions are third-party applications developed for energy modeling professionals and engineers. EcoDesigner Star is the first architectural BIM software tool capable of producing calculation results that match the accuracy of high-end building energy modeling software solutions. These graphs show the results of the other ASHRAE 140 building envelope test cases. You can see that EcoDesigner Star, represented in red, is capable of producing results that are just as accurate as the standard reference results generated with other high-end building energy analysis software applications. Let's summarize what you've seen today regarding building energy model calibration. We started by obtaining the energy performance documentation of the reference building. The reference documentation in our example is an ASHRAE 140 standard test case. As the next step, we created a building with ArchiCAD and assessed the building's energy-related characteristics using EcoDesigner Star. We then ran the energy simulation and compared the calculated results with the reference results documented in the ASHRAE 140 standard. Graphisoft EcoDesigner Star is capable of analyzing multiple thermal block building energy models and modeling conditioned and unconditioned spaces. EcoDesigner Star complies with the ASHRAE 140 standard method of test for the evaluation of building energy analysis computer programs. This standard is used for validating energy simulation software. Compliance with this standard ensures that EcoDesigner Star can be used to perform complex dynamic building energy analyses successfully, and that EcoDesigner Star produces results that are accurate enough for energy performance rating according to LEED, Green Star, and other relevant green building standards. Please remember, it's only possible to generate accurate building energy evaluation reports with a standard compliant software solution such as EcoDesigner Star. However, using a compliant solution alone cannot guarantee that your calculation results will also be accurate. The accuracy of the reports greatly depends on the quality and accuracy of the input data you provide when you create the building energy model. Therefore, in order to make sure that your energy-related design input and output is correct and precise, please calibrate each BEM carefully using reliable reference data.